Today I'm going to talk more about exponents. Anne's going to look at some problems where she combines the rules of exponents and does multi-steps. And then Steve's going to look at polynomials and some exponent problems. In Lesson 8, Anne's going to introduce scientific notation, which is an application of exponents. And then Steve's going to do some word problems involving scientific notation. I'm going to end Lesson 8 with a review of Lessons 4 through 8. We know that exponents are difficult for a lot of people, so we want to spend a lot of time working through these. In this part of the lesson, I'm going to look at one last exponent rule. Then I'm going to review the exponent rules and definitions that we've seen in previous lessons. And then I'm going to do a final summary of all the rules and definitions of exponents. So let's start with one last exponent rule. Let's first think about what the quantity a over b cubed really means. Well, this means that we have three factors of a over b. And we can write this as a times a times a over b times b times b, which simplifies to a cubed over b cubed. This is what we call the quotients to powers rule. A over b raised to the power m equals a to the m over b to the m for b not equal to 0. Notice what this rule tells us is that exponents distribute over division, just like exponents distribute over multiplication. Let's look at an example of this rule. Let's say we want to simplify 2/3 cubed. Well, using our quotients to powers rule, this is 2 cubed over 3 cubed. 2 cubed is 8, and 3 cubed is 27, so we have 8 27ths. Now let's simplify y cubed over x squared to the 4th power. Since the quotients to powers rule tells us essentially that exponent distributes over division, we can distribute the exponent of 4 to the numerator and to the denominator. Now we can apply our powers to powers rule, which tells us to multiply the exponents. So y to the 3 times 4 would be y to the 12th, and x to the 2 times 4 would be x to the 8th. Now let's simplify 5y over 3z squared. So if I distribute the exponent of 2 to the numerator and denominator, I have 5y quantity squared over 3z quantity squared. Our products to powers rule tells us that the exponent 2 distributes over the factors in the product, which means I have 5 squared y squared over 3 squared z squared. Looking back to our original expression again, notice that this exponent of 2 distributed to every factor inside the parentheses, because exponents distribute over both multiplication and division. So let's simplify. In the numerator, we have 25y squared, and in the denominator, we have 9z squared. Now let's simplify 4a squared over 5b to the 4th, that whole quantity cubed. Well, thinking about the fact that that exponent of 3 needs to be distributed to every factor inside the parentheses, we can just rewrite this as 4 cubed times a squared cubed over 5 cubed times b to the 4th cubed. So in one step, I've applied both the quotient to powers rule and the product to powers rule. 4 cubed is 64, so I have 64a to the 6th in the numerator. 5 cubed is 125, so I have 125b to the 12th in the denominator. Now let's simplify x over y, all raised to the power negative 3. So distributing the exponent to the numerator and denominator, I have x to the negative 3 over y to the negative 3. One of the things we talked about in a previous lesson is that if you want to change a negative exponent to a positive exponent, you need to move a negative exponent from the numerator to the denominator and vice versa. For instance, in this case, I see a negative 3 as the exponent in the numerator. So if I move x to the negative 3 to the denominator, it becomes x to the positive 3. Likewise, if I move the y to the negative 3 up to the numerator, it actually becomes y to the positive 3. So this simplifies to y cubed over x cubed. Well, there's another way I could have thought about this problem. I could actually apply my power to a power rule in reverse. I could write the fraction x over y all raised to the negative 3 as the fraction x over y all raised to the negative 1, and then this entire thing cubed. Remember, the powers to powers rule tells us to multiply the exponents. If I multiply the exponents here of negative 1 by 3, I get this exponent of negative 3 that I started with. Now when we raise something to the negative 1 power, it's just telling us to take the reciprocal. So x over y all raised to the power negative 1 simplifies to just y over x. So I have y over x quantity cubed. And using our quotient to powers rule, that reduces to y cubed over x cubed. But before moving on, I want to point something out here. We started with x over y all raised to the negative 3 power. In this step, I have y over x raised to the power positive 3. So to make this exponent of negative 3 positive, I needed to take the reciprocal of what was inside the parentheses. This leads to a consequence of the rules. A over b to the negative m equals b over a to the positive m, provided that a and b are not equal to 0. Again, to change that negative exponent on the outside of parentheses to a positive exponent, we need to take the reciprocal of what's inside the parentheses. Let's try this. Let's simplify 7/2 to the negative 2. So using our new consequence, I can change this to 2/7 to the positive 2. Distributing that exponent, 2 squared is 4, and 7 squared is 49. Let's try another one. What if I want to simplify negative 1/2 to the negative 5? Well, the reciprocal of negative 1/2 is negative 2 over 1, which is just negative 2. So I have negative 2 to the positive 5. When I multiply negative 2 by itself 5 times, I have 5 factors of a negative number, so I know my result should be negative. And then 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So I get negative 32. What about 7y over 3z raised to the power negative 2? Again, to make that exponent of negative 2 a positive 2, I need to take the reciprocal of what's in parentheses. So that would be 3z over 7y to the positive 2. Exponents distribute over both division and multiplication. So I have 3 squared is 9, z squared over 7 squared is 49, y squared. Now let's simplify 4ab squared over 3a to the negative 1b. There are several rules of exponents I'm going to use in this problem. Remember, when that happens, there are different orders we can do the problem. As long as we apply the rules and definitions of exponents correctly, we should come out with the right result. In this case, I'm going to ignore that exponent of negative 3 on the outside of the parentheses for a minute, because I notice that there are a's in both the numerator and denominator of the fraction, and b's in both the numerator and denominator of the fraction. So I'm going to simplify what's inside parentheses first, and then worry about that exponent. So looking inside parentheses, that 4/3 is going to remain 4/3. The 4 has an implied exponent of 1, and the 3 has an implied exponent of 1. So I don't need to do anything with that. Next, I'm going to focus on my factors of a. I have an a in the numerator, and I have an a to the negative 1 in the denominator. Remember, simplified form doesn't have negative exponents. I can make this a to the negative 1 in the denominator a to the positive 1 by moving it to the numerator. That will give me 2 factors of a in the numerator, which I can write as a squared. Now I want to focus on the factors of b. I have b squared in the numerator and b in the denominator. If I cancel this factor of b in the denominator with one of the factors of b in the numerator, that's going to leave me with one factor of b in the numerator. And all of this is still raised to the power -3. To make that power -3 a positive 3, I need to take the reciprocal of what's inside parentheses, which would be 3 over 4a squared b. So now this is all raised to the power +3. Exponents distribute over both division and multiplication. I just need to distribute that exponent to every factor inside the parentheses. 3 cubed is 27. 4 cubed is 64. A squared cubed is a to the 6th. And I have b cubed. So we end up with 27 over 64 a to the 6th b cubed. This is getting a bit complicated. If you're having troubles following along, it's probably that you need to review the properties and rules of exponents. So let's go through those. We had a lot of rules and definitions for exponents. The first one we learned was the product rule. B to the m times b to the n equals b to the m plus n. When we have the same bases, we add the exponents. Let's look at a couple of examples. Let's say I want to simplify x to the 71, x to the 8th. Well, this is just x to the 71 plus 8, which is x to the 79th. Let's think about why this rule works. If I have a to the 5th and I'm multiplying that by a, that means I have 5 factors of a, and I'm multiplying that by another factor of a. So altogether I have 6 factors of a. And we can think of that as just adding the exponents 5 and 1. Then we had the powers to powers rule. This is when we multiply exponents. B to the m raised to the nth power equals b to the m times n. Let's look at some examples. Let's simplify the expression m cubed to the 40th power. The powers to powers rule tells me to multiply the exponents. So this is m to the 3 times 40, which is m to the power 120. Now let's think about why the rule works again. If I have x squared cubed, what does this mean? I have 3 factors of x squared. So x squared times x squared times x squared. Altogether then I have 6 factors of x. 2 times 3 is 6. We multiply exponents when we have a power to a power. Then we looked at the products to powers rule. This says that a power of a product is the product of the powers. Let's look at an example. If I have x squared times y, all raised to the 4th power, this is the product of the powers, so x squared to the 4th times y to the 4th. The other way we can remember this is exponents distribute over multiplication. This simplifies to x to the 8th, y to the 4th. Let's think about why this rule works. If I had 3a to the 4th all squared, what does this mean? Well, this means I have 2 factors of 3a to the 4th. So that's 3a to the 4th times 3a to the 4th. And if I use the commutative and associative properties of multiplication, I can write this as 3 times 3 times a to the 4th times a to the 4th. That's 3 squared times a to the 4th squared. Again, notice that essentially that exponent of 2 distributed over the factors 3 and a to the 4th. And of course this simplifies to 9a to the 8th. We also looked at the quotient rule. When we have a quotient of powers, we subtract the powers. X to the m over x to the n equals x to the m minus n, provided that x does not equal 0. We have to make this exception because we can't divide by 0. So let's simplify x to the 21st over x to the 15th using our quotient rule. Well, our quotient rule says subtract those exponents. That's x to the 21 minus 15, which is x to the 6th. Let's think about why this rule works. If I have t to the 5th over t squared, what I have here is 5 factors of t in the numerator and 2 factors of t in the denominator. If I cancel those 2 factors of t in the denominator with 2 of the factors of t in the numerator, I'm left with 3 factors of t, which I can write as t cubed. Again, we can think of this as t to the 5 minus 2. We're subtracting exponents. We've taken those 2 factors of t in the denominator and canceled them with 2 of the factors of t in the numerator, leaving 3 factors of t. Then we had a definition for 0 exponents. Any non-zero number raised to the 0 power equals 1. Let's look at a couple of examples. If I raise negative 5 to the 0 power, since negative 5 is a non-zero number, the result is 1. Well, what about the opposite of 5 raised to the 0 power? This one we need to be careful on. We need to think about the order of operations. The order of operations tells me I need to apply exponents before I can negate. So the first thing I have to think about in this problem is raising 5 to the 0 power. That 0 power doesn't apply to the negation symbol in front of the 5. 5 to the 0 power is 1, but I need to take the opposite of that. Let's think about why this definition works. If I have t squared over t squared, a lot of you are probably thinking, well, obviously that's 1. When I divide a number by itself, I get 1. But what if we think about this in terms of the quotient rule? The quotient rule tells us to subtract the exponents. So this would be t to the 2 minus 2, which is t to the 0. Since I got different results starting with the same expression, t squared over t squared, it must be the case that t to the 0 equals 1, which is where our definition of 0 exponents come from. The only exception here we have again is that t cannot equal 0 because we can't divide by 0. Another definition that we have is for negative exponents. X to the negative m equals 1 over x to the m for x not equal to 0. Let's look at some examples. What if I have the quantity 3x raised to the power negative 4? Well, this should be the same as 1 over 3x raised to the power positive 4. That's 1 over 3 to the 4th, which is 81, x to the 4th. What about 3x to the negative 4? Here we have to be careful, again thinking about the order of operations. The order of operations tells us to apply exponents before we multiply. So that exponent of negative 4 only applies to the x, not the 3. So what I have here is 3 times x to the negative 4 is the same as 1 over x to the 4th. So I have 3 over x to the 4th. Let's think about why the definition of negative exponents works. If I have t squared over t to the 5th, that means I have 2 factors of t in the numerator, and I have 5 factors of t in the denominator. If I cancel the 2 factors of t in the numerator with 2 of the factors of t in the denominator, that leaves behind 3 factors of t in the denominator, which I can write as t cubed. And it leaves behind a 1 in the numerator. T divided by t is 1. T divided by t is 1. 1 times 1 is 1. But if I think of this in terms of the quotient rule, t squared over t to the 5th, according to the quotient rule, we subtract exponents. So this is t to the 2 minus 5, which is t to the negative 3. So it must be the case that t to the negative 3 equals 1 over t cubed. Again, our only exception being that t cannot equal 0 because we can't divide by 0. A consequence of the definition of negative exponents tells us that 1 over x to the negative m equals x to the positive m, again provided that x does not equal 0. Let's look at an example. 1 over 5 to the negative 2, we can simplify quickly as rewriting that as 5 to the positive 2. 5 squared is 25. But let's think about why this consequence works. 1 over t to the negative 6. If we just go back to our rule for, or our definition of negative exponents, t to the negative 6 is the same as 1 over t to the positive 6. So we have 1 divided by the fraction 1 over t to the positive 6. We can rewrite that as a multiplication problem if we multiply 1 by the reciprocal of 1 over t to the 6th, which is t to the 6th over 1. Simplifying, we just have t to the 6th, which shows where this consequence of the definition of negative exponents comes from. A consequence of the quotient rule for exponents says that x to the m over x to the n equals 1 over x to the n minus m, provided that x does not equal 0. We generally use this consequence if the exponent in the denominator is larger than the exponent in the numerator. Let's look at an example. In the expression x to the 7 over x to the 19, our exponent in the denominator, 19, is definitely larger than the exponent of 7 in the numerator. So this is 1 over x to the 19 minus 7, which is 1 over x to the 12th. Let's think about why this works. If I have t squared over t to the 5th, well, again, this is just 2 factors of t in the numerator and 5 factors of t in the denominator. Canceling those 2 factors of t in the numerator with 2 of the factors of t in the denominator leaves behind 1 in the numerator and 3 factors of t in the denominator, which is t cubed. Essentially, this exponent of 3 comes from subtracting the exponent of 2 in the numerator from the exponent of 5 in the denominator. So now I want to go through a summary of all of the rules and definitions of exponents that we've had in this lesson and previous lessons. It's very important for you to commit the rules of exponents to long-term memory, not just your short-term memory. As you take more math or science or business classes, exponents are never going to go away. They keep coming up over and over and over again. So let's look at a summary of the exponent rules and definitions. If m and n are integers and a, b, and c are real numbers, then the product rule tells us a to the m times a to the n equals a to the question mark. Do you remember what should be there? You should. This is the rule that tells us to add the exponents. If you don't remember this, this is one of the rules that you need to review. What about a power to a power rule? A to the m raised to the nth power is a to the question mark. Do you know what goes in place of that question mark? You should. It's m times n. When we have a power to a power, we multiply exponents. What about our power of a product rule? ab all raised to the m power equals what? A to the m times b to the m. This is the rule that tells us exponents distribute over multiplication. What about our quotient rule? A to the m over a to the n equals a to what power? Do you know this one? It's a to the m minus n. What about a power of a quotient? A over b all raised to the power m. What does this equal? It's a to the m over b to the m. This is a rule that tells us that exponents distribute over division. What about our definition of zero exponents? A to the 0 equals what, as long as a is not 0? Again, this is one you should know. This is equal to 1. And our definition of negative exponents? How can we simplify a to the negative n? Do you remember this one? It's 1 over a to the positive m. Again, provided that a does not equal 0. Then we had some consequences of the rules and definitions of exponents. Now it's very, very important, as I mentioned, that you have all of the rules and definitions of exponents memorized. If you forget some of these consequences, it's okay because these really are consequences of the rules and definitions. What these consequences help with is they save some steps when you're doing multi-step problems. So it's a good idea to try to memorize them, but if you don't, you can always go back to the rules and definitions to help you solve the problem. If we have a over b raised to the negative m, how can we simplify this quickly? Well, we take the reciprocal of a over b, which is b over a. Now this is raised to the positive m. What about a to the m over a to the n? Well, you might be looking at this and saying, this looks like the quotient rule. Well, one of our consequences is what we use when m is less than n, when the exponent in the numerator is less than the exponent in the denominator. Then we can simplify this as 1 over a to the n minus m. If you have 1 over a to the negative n, what's a quick way to simplify this? This is just a to the positive n. Hopefully you have all of these rules and definitions of exponents memorized, and when those question marks came up, you were quickly able to fill those in. If you weren't, you probably need to pause the tape at this point, go back and review some of the properties before watching the next segment, because Anne's going to be doing some multi-step exponent problems, and if you don't have these rules and definitions down, you're not going to be able to follow along with her.
As promised, I'm going to do a lot of examples applying all the rules of exponents. Some of these examples will seem like quite a workout. That's why we've called this part of the lesson Exponential Aerobics. So, as promised, I'm just going to start by applying the rules, but then we're going to back up a little bit and talk about arithmetic. We're going to talk about evaluating numerical expressions involving powers and evaluating powers on the calculator. So here's our first example. And when you look at a problem like this, you really need to think about what rules are needed in the example. So here there's a lot going on. First thing I notice is I have a product raised to a power. I'm going to need the product to powers rule. When I do that part, I'm also going to have to raise a squared to the third power. I'm going to use the powers to powers rule. And finally, I'm going to have a bunch of different powers of a, which I'm going to combine using the product rule. So I see at least 3 rules that I can use to solve this problem. Let's just work through the steps. 3a squared cubed times 5a cubed squared. I'm going to start by distributing the exponents to each factor in the base. So I have 3 cubed. A squared cubed, that's a to the 6th, there's my powers to powers rule. 5 squared, that's 25. A cubed squared, that's a to the 6th. Multiplying the constant factors here, 27 times 25, think about this a little bit. 25 times 25, that's 25 squared, that's 625. And I have 2 more factors of 25 I need to consider. That's going to give me 50, so I'm going to have 675. And then a to the 6th times a to the 6th. In that situation, I add the exponents, and I get a to the 12th. Another example. What rules are going to be needed in this example? Well, again, I'm going to be using the product to powers and the power to power rule. But I'm also going to be dividing some powers of x and y. I'm going to be using the quotient rule as well. So let's do it. 16 times xy squared raised to the 5th power all over 2x y to the 4th squared. So using my product to powers rule first, notice that 16 doesn't have an exponent, so I'm just going to leave it as is, and I'm going to raise x to the 5th power, y squared to the 5th power, that's y to the 10th. 2 to the 2nd power, I'm in the denominator now, 2 squared is 4, x squared, y to the 8th. Now I'm going to use the quotient rule. I'm going to do 16 divided by 4, no exponent rule there really. I'm going to look at the powers of x and the powers of y separately when I'm doing my calculation. So I have 4x cubed, that came from subtracting the exponents, 5 minus 2, and finally y squared. Another example. Notice now I have a negative exponent. I also have a quotient raised to a power. Now I'm going to use one of the consequences of the definition of negative exponents that Candace discussed in the last lesson. This is that when I have a fraction raised to a negative integer exponent, that's the same as considering the reciprocal of the fraction raised to a positive exponent. I'm going to use this rule in this example. So I have y to the third over x squared all raised to the negative 3 power. That's the same thing as the reciprocal of the base, x squared over y cubed raised to the positive 3 power. Now I can distribute the exponent of 3 over the quotient. X squared cubed is x to the 6th. Y cubed cubed is y to the 9th. Here I have a very complicated expression. All raised to the negative 1 power. Now the negative 1 power is an indication that I'm going to take the reciprocal of that expression inside the parentheses. Now I could do that right away, or I could simplify the expression inside of parentheses first. I think I'm going to do that before I take the reciprocal. So let's look at what I have. 3, I'm going to leave that alone. I have x to the 12th divided by x to the negative 8. I could subtract the exponents. 12 minus negative 8 is 20. So I have x to the 20th. Y to the negative 3 divided by y to the 4th, I could think of y to the negative 3 is giving me 3 more factors of y in the denominator, so I have y to the 7th. Now I'm going to take the reciprocal, indicated by the negative 1 exponent. So I have y to the 7th all over 3x to the 20th. Here's another example. In this example, there are many negative exponents. There are several different ways we can approach this problem. I'm going to start by just writing things out here. And as I'm rewriting the problem, I want to note that as you gain experience working these types of problems, you see that one strategy might be a little bit quicker than another strategy. Now, if I do a strategy that takes 5 steps, and you did it using a strategy that required only 3 steps, that's great. Sometimes I may choose a strategy that's a few fewer steps than a strategy you choose. With experience, though, you start to learn which might be the fastest way to work a problem. One of the things I notice about this problem is if I just applied the powers to power rule and the product to powers rule, when I multiply exponents, I'm going to end up with a lot of positive exponents, which are nicer to work with. So I'm going to just start by, in the numerator, distributing this exponent of negative 3 to each factor in the base. So I have 4 to the negative 3, m to the positive 15, n to the positive 3, all over m squared n to the 4th. So with the exception of the factor 4 to the negative 3, I've got a lot of positive exponents. Now 4 to the negative 3 is the same thing as 1 over 4 cubed. Now with my powers of m and my powers of n, I can just apply the quotient rule. I have m to the 13th, and then I have 1 factor of n in the denominator when I simplify. Only thing that's left to do is some arithmetic. 4 cubed is 64, so I end up with m to the 13th power over 64n. You may want to try this problem and see if you can do it applying the rules in another order and come up with the same result. Now here's a problem that's a little bit different than some of the ones we've looked at already. One of the things I notice when I write down this problem is that the exponent on the large base in the numerator and the base on the denominator is the same. I have an exponent of 2 on the expression in both the numerator and the denominator. And I can actually apply the quotient to powers rule in reverse here. Let's just review the quotient to powers rule. That tells us that if I have a over b squared, for example, I can write that as a squared over b squared. Well, I'm going to use this going the other way. I'm starting with something that looks like this. I'm going to rewrite it as a over b squared. Look what happens when I do that. Inside the parentheses, I have an expression that I can simplify before I square. So that's what I'm going to do. 16 divided by 4, that's 4. X to the 4th over x to the negative 4, that's x to the 8th. Y to the negative 2 divided by y cubed, that leaves 5 factors of y in the denominator. This is the expression I'm going to square. Squaring the 2 factors in the numerator and the expression in the denominator, I have 16 x to the 16th, y to the 10th. So here we have u squared v to the negative 3 to the negative 1 power times u to the negative 1 v squared all cubed. This is all over u to the negative 4 v squared. Again, a couple of different things I can do to start here. I think this time I'm going to take that first expression. In the numerator, I recognize that I'm looking at the reciprocal of u squared v to the minus 3. I think I'm going to move this expression down to the denominator. So I have u to the negative 1 v squared cubed over u squared v to the negative 3 u to the minus 4 v quantity squared. Now I'm going to apply the product to powers rule. Multiplying exponents, u to the negative 3 v to the 6th over u squared v to the negative 3 u to the negative 8 v squared. In the denominator, I can use the product rule. U to the negative 3 v to the 6th, 2 plus negative 8, that's negative 6, v to the negative 1. And now let's think about what I have here. If I subtract using the quotient rule, negative 3 minus negative 6, that's positive 3. So I have u cubed v to the negative 6 divided by v to the negative 1. This v to the negative 1 factor will move to the numerator, leaving me 7 factors of v. I started with a very complex expression, and it's simplified to u cubed v to the 7th. For those of you who are going on to take more mathematics classes, this is a very useful skill. If you had to work more with the original expression you were given, it would be much easier to work with the simplified form u cubed v to the 7th than the original expression. So now, after doing all that algebra, we're going to go back to some arithmetic. Now here's a problem involving powers where there aren't any variables. And the reason why we're going to practice this is that we learn all of these rules of exponents, and in time we become very good at applying the rules of exponents when we're working with a lot of variables. Sometimes, though, the arithmetic is what we forget how to do. So I want to just work with a couple of arithmetic problems to kind of recall how to do the arithmetic parts of these powers. So here I'm going to simplify the expression, the opposite of 3 squared plus 4 squared all over negative 2 quantity squared minus 3. Now, I just put this expression up here to remind us that there is a difference between the opposite of 3 squared and negative 2 quantity squared. We know the order of operations is different in evaluating these two expressions because of the parentheses around -2. So I have -9 plus 16 all over 4 minus 3. -9 plus 16, that's 7. 7 divided by 1 is just 7. Now let's go work with some negative exponents and arithmetic. We have the expression 3/5 raised to the -3 power. Now when we're doing arithmetic, we can do absolutely nothing to evaluate a power with a negative exponent. We have to change this into some problem with a positive exponent because we know what positive integer exponents means, telling us how many factors we have. Then we can do a calculation. So the first thing I'm going to do is apply my exponent rules so I have something to evaluate here. Remember, 3/5 raised to the -3 power is the same thing as the reciprocal of 3/5 to the +3 power. Now I can do some arithmetic. This is 5 cubed over 3 cubed. Now we're going to evaluate some algebraic expressions. We're asked to evaluate x raised to the -5 power for x equals -2. So if x equals -2, then the algebraic expression x to the -5 equals -2 raised to the -5 power. Now before I go any further, we've gotten into the habit of writing our bases, if they're negative, in parentheses. Also, when I have a negative exponent, I have to change the problem so that I have a positive exponent so I can actually evaluate this expression. So -2 raised to the -5 power, that's the same thing as 1 over -2 to the +5. Now I can evaluate what is 5 factors of -2. Well, that's -32. Another arithmetic problem. We're looking at 12 times 10 to the -3 all over 3 times 10 to the -9. Now when I do this problem, I have 12 over 3, and I also have the quotient of 2 powers of 10. I think I'm going to do those separately. So 12 divided by 3, that's 4. And when I subtract the exponents on the powers of 10, I end up with 4 times 10 to the 6th. And 10 to the 6th, well, that's 1 with 6 zeros after it. So this is just 4 million. Another problem, we have two different algebraic expressions, and we're going to evaluate them for x equals 4 and x equals -2. And we have a warning here. We need to remember that exponents do not distribute over addition or subtraction. We have very different problems here. The first problem, x plus y to the -1, that's the reciprocal of the sum of x and y. Whereas this expression, x raised to the -1 plus y raised to the -1, that is the sum of reciprocals. Reciprocal of a sum, sum of reciprocals. When we work through the problem, we're going to see that we'll get different results. So, if x equals 4 and y equals -2, then let's look at the reciprocal of the sum. X plus y to the -1 power, that's 4 plus -2 to the -1. 4 plus -2, that is 2 to the -1, and the reciprocal of 2 is 1/2. On the other hand, x to the -1 plus y to the -1, that's the reciprocal of x, which in this case is 1/4, plus the reciprocal of y, which is plus -1/2. And when I subtract 1/2 from 1/4, I get negative 1/4. You can see here, once we do some arithmetic, that the reciprocal of the sum is not equal to the sum of reciprocals. Finally, we just want to take a few minutes to talk about evaluating powers on a calculator. I'm going to do this problem by hand, but then I'm going to do it on a calculator so we can make sure that we're getting the numbers we would expect from our calculator. So if t equals 2, then the expression t to the negative 3 is 2 raised to the negative 3 power, which is 1 over 2 cubed, which is 1/8. I'm going to perform this operation on a couple of different types of calculators. I'm going to start with a scientific calculator. Now on my calculator, I have a power key here that says x raised to the a power. Some calculators have x to the b, a to the b, x to the y. The important thing is that you find your power key on your calculator. If I'm going to enter this on my calculator, I'm going to evaluate 2 raised to the negative 3 power. So I'm going to hit my power key. On this calculator, I put in the integer and then change the sign, and that gives me 0.125. Is that 1/8? Well, it is. If you want to check, you could just do 1 divided by 8. That's 0.125. Let's try this on a graphing calculator. On the graphing calculator, I have what's called a caret key for evaluating powers. So the way I'm going to evaluate 2 to the negative 3 on this calculator is I enter my base, and I enter my caret key to indicate that I'm raising the 2 to a power, and then I put in negative 3. So on this calculator, I put in the minus sign before I put in the 3. And that's 1/8. My calculator gave me a fraction in this case. So now let's work some problems where you would probably pull out a calculator rather than working these with pencil and paper. So same expression, but a different value for the variable. If t equals 1.4, then t to the negative 3 equals 1.4 to the negative 3. Now I'm going to pull out my calculator to see what that is. So 1.4, I'm going to raise that to the negative 3 power, and I'm going to round this off. That's about 0.36. Let's do another one. Now we want to evaluate t to the negative 4 power for t equals negative 0.56. So if t equals negative 0.56, then t to the negative 4 equals negative 0.56 to the negative 4. Notice I put the base in parentheses. Put the base in parentheses when I'm writing things out on paper. I'm going to put my base in parentheses when I enter this into the calculator as well. So first entering the base and putting them in parentheses, I have 0.56, make it negative, put that in parentheses, and I'm going to raise this to the negative 4 power. So using my power key, I put in the 4, make it negative, there's the result. This is approximately 10.2. Let's try it again. Lots of negative signs in this problem, so we need to be very careful. If t equals negative 0.16, then the opposite of t to the negative 4. That's the opposite of t, which is negative 0.16 raised to the negative 4 power. Let's see what our calculator says this is. So let's be careful. when I said this, I said the opposite of all of this. So the first thing I'm going to do is I'm going to evaluate this expression and then take the opposite. So putting that base in parentheses, 0.16, make it negative, put it in parentheses, raise that to the -4 power. So I put in my 4, make it negative. There is this expression, and then finally I need the opposite of that. So you have to be quite careful with the opposite key and the negative key on your calculator. So this becomes approximately negative 1,525.9. One last thing about the calculator. We've been talking about the -1 power as a reciprocal. So if I wanted to find the reciprocal of 3.2, I could write that as 3.2 to the -1 power. Let's look at our calculator, and we're going to look at both. This scientific calculator has a reciprocal key in the form 1 over x. We now know that x to the -1 is the same thing as 1 over x. So on this calculator, to find a reciprocal, I'm going to use the 1 over x key. So if I do 3.2 reciprocal key, I find the reciprocal of 3.2. That is equal to 0.3125. Could I have gotten that same result another way? Well, if I just typed it in the way it is on my paper, 3.2 raised to the -1 power, that's the same thing. On your calculator, you might actually have a key that looks like this, x to the -1. That would be your reciprocal key. So that ends this part of the lesson. Steve's going to come and review things about both exponents and polynomials.